Okay, so f of x is just, if you think of the slope-intercept line equation, this has a y-intercept is 0 because it's going right through this origin. The slope is the height divided by the width. So the function is just h over L times x. And so the centroid of one of these increments in area is x, and then hx over 2L, going from this formula. dA is the height, hx over L, times the width, dx, of one of those little slivers. And so you end up with an integral from 0 to L of x hx over 2L times hx over L dx. Oops. What did I miss? We have the integral from 0 to L, x, and then hx over 2L. Okay, so now to do this integral, it's two independent, you can think of it as two independent integrals. So you have the integral from 0 to L of h x squared over L. That's the x component, dx. And then the y component is h squared x squared over 2L squared dx. We're integrating with respect to x. So for the top one, that gives you hx to the third over 3L. And for the bottom one, that gives you h squared x to the third over 6L squared. This isn't an integral anymore. And we're evaluating it from x equals 0 to x equals L. And so if you plug in L for x, you get h L to the third over 3L. And here you get h squared x, let's see, h squared L to the third over 6L squared. You can cancel. Oh. Yeah, I forgot something important. So this equation is, for the centroid, we need to divide by the area. And so you get, so this is 1 over A, 1 over A, 1 over A, 1 over A. The area of the triangle is HL over 2. And so you get 2 over HL times HL squared over 3. And for the y component, h squared L over 6. For the top one, the L cancels one of those L's, the H cancels the other one, so you get L, so 2L over 3. And for the y component, you get 2H over 6. So 2L over 3, and then H over 3. Any questions about that? Okay, so with all of these, if you ever have to do one of these integrals, the tricky thing about it is coming up with what your scheme is going to be to cover all the area, you know. Like if you're doing a circle, your increment in area might be a sliver, like a ring going around the circle, you know. If you wanted to try to use rings going around the outside of, you know, circular rings to define the total area of a triangle, it wouldn't work very well, you know. And so every shape that you do, the way you define that increment of area is kind of the key thing. Okay, so this is a formula that you can use for any right triangle. And I'm going to give you a few formulas that for some of the common shapes that we're going to see. Most of the time, you can use formulas rather than integration. Okay, so here are the common shapes. So if you have a right triangle, and I'll give a calculation for the area and a calculation for the x centroid and the y centroid. So for a right triangle, where this is L and this is H, what we got with the coordinate system over at the point, now I'm moving the coordinate system over, so the answers here are going to be negative L over 3, and y is H over 3. Notice physically that's the same point. And the area is LH over 2. Then the second common shape is a quarter circle. With a radius of r. With the coordinate system at the center of the circle. The area is pi r squared over 4. And the centroid is 4r over 3 pi x and 4r over 3 pi y. And then, yeah, a semi-parabolic area if this is x and this is y, then if this distance is a and this distance is h, the area is 2a, that one's cut off, 2a, I think that's 2ah over 3. And the centroid is 3a over 8 and 3h over 5. Okay, so back to the example problem. Question?
Why is it 2? It'll be smaller than the front one. It should be less than half in each, right? The area?
2,
Would that be
I guess.
concave for the convexity?
Oh, it's this one.
Yeah.
We're talking about this. Okay, yep. Back to the example problem. Did I define it? So this thing. So let's say that we have a triangular distributed load with a magnitude of 10,000 newtons per meter and a length of 2 meters. This is a pin joint and this is a roller. And we want to first calculate the reactions, and second, we want to calculate the internal loads. To calculate the reactions, free body diagram of the whole thing, we're going to ignore the weight of this beam for now. What forces are acting at the pin joint? Yep. So force vector FA. What's acting at the other end? Yep, up. Call that FB. And now that we've chosen a body to isolate, we can treat that distributed load as a point force. Where is that going to act? Yep. And so it's going to act 1/3 of the way from B. So the distance from over here is going to be, 2/3 of this distance. So it'll be here. What about the Y centroid? doesn't matter because you can always move this force anywhere along its line of action. And what's the total force? It's the area, so it's 10,000 times 2 divided by 2, so 10,000 newtons. So Newton's second law says Fax, Fay plus 0 Fb plus 0 negative 10,000 is equal to zeros. And the rotational equation, this length here is 4/3. So you have a, you don't have any moment produced by Fa. You'd have a clockwise moment produced by the 10,000 Newton force. So that's going to be negative 13,333. And then you have a counterclockwise moment produced by Fb. So Fb is equal to positive 666. Right? And then plug that in here and you get Fa is equal to 0 and then positive 333. Okay, so now we know what those external loads are. If we do a free body diagram of the whole thing, it looks like this. We have an upward force of 3,333, an upward force here of 6,667, I guess. And then we have the distributed load. And at this point, the value of the distributed load is 10,000 newtons per meter. Where are the important points on this? Only at the ends. The function describing the distributed load never changes. So we only have 2 important points. That means we only have to make 1 cut. Okay? Any questions? So cut 1. The right side of our body is going to represent x values everywhere from just more than 0 to just less than 2. So now this length is x. We're going to have this force for sure. We're definitely going to have a distributed load. But now the key thing that you have to notice is the value of this point on the distributed load is not 10,000 anymore because this beam goes on, you know. And so that distributed load goes on. This would be 10,000. But this is something else. So what's the value of the distributed load there? 10,000. Yeah, right. 10,000 over x. 10,000 over, not 10. So the slope is, okay, so think of the function that describes this line. That function is 10,000 over 2 times x. Okay? So that function, whatever x value you're at, is 5,000x. Okay? And so this is going to be 5,000x. And now all of our other calculations are going to be based on the fact that the height of the triangle now is 5,000x. It's not h. And the length is x, not L. Then we also have the tension, the shear force, and the bending moment. And now that we've chosen the body to isolate, now we can represent this distributed load as a point force. So we have 3,000. And we have a downward force. What's the area of this triangle? It's the base x times the height 5,000x divided by 2. So 2,500x squared. And this distance, if the whole thing is x, then this is 2/3 x. Any questions about that? And then we have the internal loads. So Newton's second law says 0.3333 plus 0, negative 2,500 x squared plus t negative v is equal to zeros. So there's no tension, and the shear force is negative 2,500 x squared plus 3,333. And the rotational equation, if we're calculating the moment about the left end, then there's no moment produced by the reaction force. There's a clockwise moment produced by this 2,500x squared. So that makes it a negative moment. And the magnitude of that moment is 2,500x squared times the moment arm of 2x over 3. Then there's the bending moment, the couple that we're calling the bending moment, minus Vx, and that's all equal to 0. So you get negative 1,667 x to the third plus m minus Vx is equal to 0. We're trying to solve for m. So m is equal to 1,667 x to the third plus Vx, so plus negative 2,500 x to the third plus 3,333x. And so you get m is equal to negative 833 x to the third plus 3,333x. Any questions about that? Okay, so what do we have to, what should we check?
The moment is take the
Yeah, dm dx has to be equal to v. So 3 times 833, negative 833 is equal to 2,500. Derivative of 3,333x is equal to 3,333.3. And okay, so that one checks out. And then what about tensions at the ends. There shouldn't be any tensions because there's no horizontal forces. If you plug x equals 0 in here, no, oh, the tension is 0 everywhere. And then that's easy to calculate. And then what about the shear forces at the ends? Yeah, they don't have to be 0. And then finally the bending moment. There's no point couples, so that should be 0 at the two endpoints. You can see that the moment comes out to be 0 when x is equal to 0. What about when x is equal to 2? Well, 8 times 833 is equal to 6666. Yeah, so minus 6666 plus 6666 equals 0. So that works out. Okay. Okay. So now that we can solve for the internal loads in beams, we can start talking again about stresses and strains and go into ways to calculate stresses in the presence of shear force and bending moments. So that's what we're going to start doing next time. Okay. Any questions?